There's a sound coming from outside our solar system, and NASA confirmed years ago that Voyager 2 is the instrument detecting it. What nobody told you is what that frequency actually means. Voyager 2 launched in August 1977 and has been traveling ever since. It flew past Jupiter. It flew past Saturn. It became the only spacecraft in history to make close visits to both Uranus and Neptune. Then it kept going. By November 2018, it had traveled so far from the Sun that it crossed the heliopause, the outermost boundary of our solar system, and entered interstellar space. It became only the second human-made object to do this, following its twin Voyager 1, which made the crossing 6 years earlier in 2012. And on board Voyager 2, one of the most critical instruments it carries is called the plasma wave subsystem. This instrument does something almost impossibly strange. It listens. It detects the vibrations, the oscillations, the frequencies of charged particles in the space around it. And since Voyager 2 crossed into interstellar space, what that instrument has been hearing is unlike anything recorded anywhere else in human history. The confirmation came from the University of Iowa, whose researchers led the plasma wave instrument team. When Voyager 2 crossed the heliopause on November 5, 2018, the plasma wave subsystem recorded an abrupt, unmistakable jump in plasma density. On one side of that boundary, inside the heliosphere, the plasma was hot, thin, and characteristic of the solar wind streaming outward from our sun. On the other side, the plasma was cold, dense, and completely different in character. That sharp jump in plasma density was the definitive confirmation that Voyager 2 had entered the interstellar medium, the vast ocean of charged particles and magnetic fields that fills the space between the stars. And the frequency at which the plasma wave instrument detected this new environment corresponded to an electron plasma oscillation at roughly 2 to 3 kilohertz. That number, that specific frequency, was exactly what theoretical models had predicted the interstellar medium should produce. The models were right, the instrument confirmed it, and humanity had its first direct 2-point measurement of interstellar plasma, with Voyager 1 measuring from one direction out of the solar system, and Voyager 2 measuring from a completely different direction on the other side. This matters more than most people realize, because the frequency is not just a number, it is a measurement of density. When plasma, which is electrically charged gas, oscillates, the frequency of its oscillation tells you exactly how many electrons are packed into a given volume of space. The specific kilohertz frequencies that the Voyager plasma wave instruments detected translated directly into an electron density of roughly 0.008 to 0.15 electrons per cubic centimeter in the local interstellar medium. That is far denser than the plasma inside the heliosphere, where solar wind produces densities closer to 0.02 electrons per cubic centimeter. The interstellar medium outside our solar system is, in terms of electron density, roughly 40 to 70 times more densely packed with plasma than the space inside our protective bubble. The implications of that density difference go directly to the heart of how well our heliosphere shields us from the galaxy outside. The plasma wave instrument has also been detecting something called plasma waves themselves, which are oscillations that travel through the interstellar plasma like ripples spreading across the surface of a still pond. These waves are triggered when powerful eruptions from the sun, solar storms, send shock waves blasting outward through the heliosphere at millions of miles per hour. Even after those shock waves cross the heliopause and enter interstellar space, they keep propagating. And when they do, they compress the interstellar plasma ahead of them and set it ringing at its natural frequency. The plasma wave instruments on the Voyagers detect that ringing, and from the frequency, scientists can calculate with high precision the density of the interstellar medium at that exact location in space and time. Each time a solar storm strong enough to push a shock wave all the way out to the Voyagers sends one of these ripples through the interstellar plasma. The instruments record a brief, intense plasma oscillation, a whistle in the data, a tone that carries inside it precise information about conditions 13 billion miles from Earth. In 2021, researchers published a landmark discovery in Nature Astronomy. They had found something new in the Voyager 1 data, a faint, persistent narrowband plasma wave emission that was not triggered by solar shock waves. It was just there, all the time, a continuous hum coming from the interstellar medium itself. Scientists called it a plasma line, or quasi-thermal noise emission, and it was produced by the thermal motion of electrons in the interstellar plasma, constantly interacting with Voyager's antenna. Unlike the sporadic solar shock-triggered whistles, which appeared maybe once a year and provided only a snapshot of density at a single moment, this persistent signal provided a continuous, steadily sampled measurement of interstellar plasma density over vast distances of space. Suddenly, scientists had not just scattered data points from occasional shock waves, but a continuous record. And what that continuous record revealed about the structure of the interstellar medium was deeply unexpected. The interstellar medium is not uniform. It is not a smooth, featureless ocean. It is turbulent, structured, layered, with density fluctuations that vary across scales, ranging from fractions of an astronomical unit to enormous stretches of space. The plasma frequencies Voyager 1 detected as it moved through the interstellar medium showed a radial density gradient, meaning the plasma gets progressively denser as the spacecraft moves further from the Sun. But it also showed sudden jumps, regions where the density increased sharply before settling again, evidence of pressure fronts and shock waves that had been traveling through the interstellar medium for years, perhaps generated by powerful solar activity cycles back and pushing through the boundary of the heliosphere long before they reached Voyager's position. The interstellar medium that surrounds our solar system is alive with activity that our models only partially predicted. Now here is where Voyager 2's specific plasma wave measurements become especially significant and genuinely alarming. When Voyager 2 made its crossing in 2018, it entered the interstellar medium at a completely different location from where Voyager 1 had crossed 6 years earlier. The two spacecraft left the solar system in different directions. Voyager 1 crossed the heliopause above the plane of the solar system. Voyager 2 crossed below it. The fact that both measured a sharp jump in plasma density at the heliopause and that both detected plasma frequencies in the same kilohertz range, consistent with similar electron densities, confirmed that the interstellar medium around our solar system is relatively consistent in its basic properties from one direction to another. But the differences between what the TWO probes measured were also revealing, because Voyager 2 found the heliopause at a different distance from the Sun than Voyager 1 had, and the thickness of the boundary region itself was different at the two crossing points. The heliosphere is not a perfect sphere. It is asymmetric, pushed and shaped by the pressure of the interstellar medium flowing past it at around 57,000 miles per hour relative to our Sun. The tail end of the heliosphere is stretched out behind us as we move through the galaxy, while the nose end, the direction we are heading, is compressed tighter. Voyager 2 crossed the boundary on the compressed side. The data it returned helped scientists map that asymmetry for the first time with actual in situ measurements. But here is what the frequencies detected by Voyager 2 have confirmed that scientists quietly find disturbing. The plasma density outside the heliopause, measured directly and repeatedly by the plasma wave instrument, corresponds to a pressure on the outer boundary of our solar system significantly higher than older models had assumed. Combine that with what Voyager 2's magnetometer found, an interstellar magnetic field 2 to 3 times stronger than predicted, and the picture that emerges is one of a heliosphere that is being squeezed more forcefully from outside than the scientific community believed before these measurements existed. The frequency data is not just a curiosity. It is evidence that the forces pressing against our cosmic shield are more powerful than our calculations told us. Every kilohertz measurement from the plasma wave instrument is a data point in a growing case that the interstellar environment around our solar system is more energetic and more dense than the models assumed. And now the instrument faces an uncertain future. In September 2024, NASA confirmed that it had been forced to shut down the plasma science instrument on Voyager 2, a separate device from the plasma wave subsystem, to conserve the spacecraft's dwindling power budget. The plasma wave subsystem itself remains active, but the window is closing. Engineers completed a complex power redistribution maneuver in August 2026, specifically to keep the remaining science instruments alive for at least one more year. Each transmission that comes back from Voyager 2's plasma wave instrument now is potentially one of the last direct measurements of interstellar plasma frequencies from inside the space between the stars that any human instrument will make for decades. No other probe is heading outward on a trajectory that will reach the heliopause in any relevant time frame. When Voyager 2 falls silent, the universe beyond our solar system goes quiet too, at least as far as our instruments are concerned. The frequency NASA confirmed Voyager 2 was picking up from outside our solar system is real. It is scientifically verified and peer-reviewed. It is not an alien signal, not a hidden transmission, not a coded message. It is the sound of the interstellar medium itself, a cold, dense, turbulent plasma ringing at kilohertz frequencies that tell us exactly how thick and powerful the environment pressing against our solar system's walls truly is. And what it tells us is not comforting. The walls are under more pressure than we thought. The instrument measuring that pressure is almost out of power, and the silence it will eventually leave behind is the most unsettling frequency of all. Think about what it takes to detect a frequency from 13 billion miles away using an antenna built in the 1970s. The signal Voyager 2 transmits back to Earth arrives at the deep space network antennas with less power than it would take to light a single LED on your television remote control. The engineers at NASA and the University of Iowa who read that data are filtering out noise, correcting for the Doppler shift caused by Voyager's motion, and extracting plasma frequencies from signals so faint they border on the undetectable. And from that whisper across billions of miles, They are reading the density of interstellar space to 4 significant figures. The fact that this is possible at all is one of the most extraordinary technical achievements in the history of science. The fact that what the measurements tell us is somewhat frightening is simply the universe being honest with us for the first time. The interstellar medium, the space outside our solar system, has been there forever, pressing against the heliosphere long before any instrument existed to measure it. The frequencies Voyager 2 detects are frequencies that have been vibrating in the space between the stars for billions of years. We just never had ears to hear them before. What we are learning as these measurements accumulate and as scientists compare the data from 2 probes traveling in different directions through the same interstellar neighborhood is that the space immediately surrounding our solar system is denser, more turbulent, and more energetically active than textbooks written even 30 years ago suggested. That knowledge changes the questions we ask. It changes how we think about the long-term stability of the heliosphere over geological timescales. It changes how we model the relationship between interstellar conditions and life on Earth. And it makes the coming silence of Voyager 2, whenever that day arrives, something that scientists describe not just with sadness, but with a specific scientific dread. Because everything Voyager 2 still has left to say, every frequency its plasma wave instrument still has left to detect, is knowledge that will be lost the moment that final signal fades. The universe is speaking. Voyager 2 is the only ear we have left to hear it. There's one more layer to this story that deserves to be stated clearly. In 1992, and again in 1994, the plasma wave instruments on both Voyager 1 and Voyager 2 detected something that researchers called low-frequency radio emissions coming from beyond the heliopause. These were not the kilohertz plasma oscillations triggered by solar shock waves inside or near the boundary. These were radio signals, genuine electromagnetic waves, detected while both spacecraft were still inside the heliosphere but clearly originating from somewhere outside it. Scientists traced the sources using triangulation from the 2 spacecraft and concluded the emissions were coming from the outer Helios Heath region, the turbulent zone just outside the heliopause, where the solar wind's fading influence meets the raw interstellar medium head-on. The emissions appeared to be generated by solar storms sending energetic particles crashing into that boundary region, triggering plasma oscillations that then radiated outward as radio waves. They were not alien. They were plasma physics at the edge of the solar system. But they were a frequency, a radio signal, detected by Voyager instruments and originating from outside the known boundary of our solar system, years before either probe had crossed that boundary. That is what it means when scientists say Voyager confirmed a frequency from outside our system. It is a real detection, a real confirmation. The universe beyond our solar system has a voice, and for 50 years, one spacecraft has been listening.